So hello everyone, thank you for coming to today's seminar. We have the pleasure and honor to have Alan Chau from CISPA today, who's visiting me and visiting us in the department. He's a racing star in many fields. In particular, he stumbled upon imprecise probabilities a few months ago, and that's how we became friends and our collaboration started. And in particular, today he's going to talk to you about something that the precise probabilistic community has banged their head around for a long period of time. That is how to test whether a distribution belongs to a certain set of distributions and many more. But of course, Alan, the floor is yours, so you can chime in.
So, hi everyone. Thank you for coming. Very happy to present my work here. So for today's talk, I'm going to start with a bit of my own research agenda and then dive into what actually is imprecise probabilistic machine learning trying to do. So most of those slides are copied from Michele's presentation. And then I'm going to talk about my recent submission to AI-Stats on Credal hypothesis testing. So a bit about me. I did my PhD at the Oxford Statistics Department, supervised by Dino. And then I did 2 years of postdoc at CISPA, Germany, with Krikamo Muendet, and I'm moving to Singapore in a few months to start my faculty journey. So my research interests lie within the umbrella of trustworthy machine learning. And in particular, I ask questions about like how to make machine learning more uncertainty aware, how to make them explainable, and how to integrate preferences into this kind of system. In particular, as I said, the machine learning pipeline has a lot of interesting components. And we have like hypothesis testing, probabilistic inference, optimization, or how to evaluate your model, or how to deploy your model. And in each of these separate stages or components of ML, there are many places where you can be uncertain about. And throughout my PhD and postdoc, I have contributed some to these areas. And for my second research pillar, I'm curious about how to develop explainable algorithms or explanation methods for non-explainable algorithms. And not only about explanation, but when we have explanations, what are the implications these explanations have to the learning pipeline? So these are some of my work. And my last third research pillar is about like modeling human preferences and how to incorporate human preference in machine learning. So imagine you're doing some kind of experimental design, and then you have some experts that can tell you this is a better choice than the other choice. Can you incorporate that into your experimental design setup? So that's kind of what's going on. Okay, so that's my research interest. But today I'm gonna put on the imprecise probabilist hat and talk about this type of stuff called IPML. So the motivation for considering imprecise probabilities rather than precise probabilities is quite simple. So this is a picture taken from our retreat 2 weeks ago. So let's say I want to ask my supervisor, like, do you think it's going to rain tomorrow? And when he say yes, for certainty, it kind of means that the assessment of the event raining tomorrow by Crick is 1, it's like certainty. But when he say more likely than not, this translates to his assessment being greater than or equal to 0.5. That's kind of the best you can say. You can't say anything more, right? And sometimes Crick is very fun. He will say maybe. Then in this case, I have no information I have information to talk about his belief, but it's quite factual. It's anything between 0 to 1. And how to reason under imprecision and ambiguity is kind of what the motivation behind the field of imprecise probabilities. With these kind of like giants laid out the foundation of the work. And there will be Michele 2000 something in the future. So what exactly are imprecise probabilities? So from the perspective that reasoning should start with recognition and acknowledgement of ignorance and uncertainty. So you can see that I have highlighted these two words very differently because from my perspective, ignorance is something that you don't know, but uncertainty is It's about, you know that something is being uncertain. So philosophically, they are different, and you will need different tools to handle them as well. So uncertainty is about like how likely facts or events are to happen. And a lot of us will agree maybe uncertainty is oftentimes modeled by probabilities. But when it comes to ignorance, things that we actually don't know, like we have no information about it, then a probability is not very good at describing what we don't know. So it's measured by quote unquote imprecise probabilities. And copy the definition from Michele is like, imprecise probability is a study of mathematical models that can incorporate both indeterminacy and uncertainty. So I quite like this confusion table. It's going to make you more confused later on, but there are two players in this table. One is an agent or machine learning or agent or statistician. You have the world. Okay. I'm going to say the world has deterministic events and aleatoric or uncertain or stochastic events. And from an agent perspective, I either know or I don't know. So I assume these four discrete states, and you will get this table. So for deterministic events that I'm certain of, then people often just call it certainty. For stochastic events that I know is going to be stochastic, I even know the distribution of this stochasticity, then usually people say this is risk from the finance or economics perspective, or machine learning will call this aleatoric uncertainty or representation of aleatoric uncertainty. But we can have uncertainty over deterministic event as well, because, for example, most of you will not know where I'm from or what I had for breakfast this morning, but I had it already, so it's a deterministic event. So for deterministic events, but I don't know, this corresponds to epistemic uncertainty. And most of the cases, we will have stochastic events that we don't know at all. And there's some literature called this Knightian uncertainty, but it's just a mix. Yes, please.
For those of you who were here when some statements student came and gave us a talk earlier this year, he studied Knightian uncertainty in probabilistic programming. So as Alan was saying, this is a very active area of research.
Yep. But in reality, things are not that discrete. Oftentimes you see a continuum of knowing and not knowing and randomness and extremely random events. So in the x-axis, you see the degree of randomness. On the y-axis, you see the degree of certainty or the amount of knowledge I have for certain things I care about. As we increase the randomness, we are going from problems or things that they're problematic, but there's still some trend we can capture, to things that we completely have no idea how to model because it's kind of going into messes. And people, as I defined earlier, in the part that is closer to zero, the x-axis, we have things that are still random in nature, but we have some trends we can capture. So those randomness, we call it risk. And as we go, we have like things we cannot model, so we call it Knightian. And I argue that a lot of problems in machine learning is somewhere around that region, because we don't know much about the problem, but we are not completely ignorant about the problem. We have some data, we have some prior beliefs, but we don't know that much. And in terms of randomness, there must be some kind of randomness that we can capture, right? Otherwise, we cannot solve the problem. So it's around that region, most of the problems we care about. So IPML, from my perspective, is how to bring this awareness of uncertainty and not knowing to machine learning. Example of awareness from classical statistics literature is like robust frequent test, Bayesian sensitivity analysis, and in IPML, there are a few areas or quote unquote applications that classical ML people might also care about, being cases where distribution is not specified correctly. One thing people always say is like, we assume our data is RID from a PXY, and then we do all the fancy stuff after this statement. But what if the first statement is already wrong? So this corresponds to the literature on domain generalization, distributionally robust optimization. We also want to make prediction, but maybe not so certain about a point prediction, but we are happy to give a set of predictions. Those related to conformal or version-based learning. We also want to quantify, propagate, or disentangle different types of uncertainty in the whole machine learning pipeline. There could be parameter uncertainty, data uncertainty, optimization uncertainty, algorithmic choice uncertainty, deployment uncertainty. These are all uncertainties that are maybe worth studying, but they're often just put inside the heads of epistemic and no one cares about them. Lastly, some area that I'm also trying to contribute a bit is when we do statistical procedures like testing or decision-making, there are certain parts that are never going to be able to justify subjective choices. Then in those cases, how should we rationally, as an agent, rationally express our uncertainty or imprecision in those cases? So it's kind of like human-centric ML, right? So there are some classical attempts in IPML on these domains and by these giants. And in recent years, there are more ML-flavored IPML stuff as well. These slides contain stuff that are mostly on prediction or learning, things that ML people mostly care about for some reason. But other than prediction, there are other domains of ML that's interesting as well. And today I'm going to talk about hypothesis testing. So I hope that gives an overview on IPML. And now I'm going to put on the ML scientist hat and talk about how should we test hypothesis under dataset uncertainty. So first of all, what is dataset uncertainty that I'm talking about? So there are a few examples. First example is distribution shift. Imagine you train an algorithm using data from New York, but you have to apply it to patients in Thailand. So there's a shift of distribution from the training and the testing environment or the application deployment environment. And second example is when you have multiple relevant data sets acting as proxies to something you care about. So it sounds cryptic, but what it actually means is, imagine the German government wants me to do some inference on the population of German citizens at blood sugar level. So the right way to do this is to get every existing German still alive and then do the procedure. But this would be too costly. And in reality, what happens is a lot of people will go and collect different data sets from, for example, hospitals across the country. And in that case, I argue doesn't really make sense to assume all these hospitals share the same distribution. I'm willing to assume that the patients from the same hospital will share our IID sample from the distribution respect to the hospital, but overall, I don't think all the hospitals share the same distribution. But they are all relevant to what I care about, which is the population of the German blood sugar level. Otherwise, I wouldn't collect these data sets in the first place. They must be relevant. Example 3 is on collective decision-making. So we know that Safesh has shown some results that if a person has some rational preferences over some item set, it corresponds to having a probability distribution over the items. And in this case, when we have a collection of people making collective decision-making, in the sense expressing their preferences per person, then per person you get a distribution. So you have, in some sense, a distribution uncertainty as well. So I hope that those are like examples of where dataset/distribution uncertainties can arise. And today I'm going to present this work on Credal two-sample tests of epistemic uncertainty. And they are from my collaboration with these amazing people. So a bit of recall about what statistical hypothesis testing is about. It's about when you observe some data, IID from a distribution, you want to evaluate whether these observations provide sufficient evidence to reject some definition or some assumption about the distribution you care about. So I repeat, you are willing to assume the data is IID from P, and then you want to see if there is sufficient evidence solely from the data alone that allows you to reject some statements about P. That's statistical hypothesis testing. Usually we have two players. We have the null hypothesis, and then we have the alternative hypothesis. So a lot of my work, or the type of hypothesis testing in non-parametric hypothesis testing in ML, is the Fisherian type of hypothesis testing, which means we only reject the null. We're not doing likelihood ratio tests comparing hypotheses. We're only rejecting the null. So, but that's technical detail. But usually the null hypothesis and the alternative hypothesis they don't overlap. And hypothesis testing is quite useful because it allows you to make informed or justified decision based on data alone and some assumptions. And it has many applications, for example, in A/B testing or in goodness of fit testing, where you collect some data, you want to know whether this data is actually from a normal. Then you can do this kind of goodness of fit to check. You can use conditional independence test for causal discovery, and you can even use it for like treatment effect testing, checking whether distribution after being subscribed to some drugs actually has statistically significant changes compared to before they do the treatment effect, So a typical testing procedure constitutes the following. You first need to formulate your hypothesis, and then you need to find a test statistic. You need to compute it, and this test statistic should be chosen such that it is small when your null hypothesis holds. In this case, if the null hypothesis doesn't hold and you see a very large test statistic, then you have a lot of evidence to allow you to reject the null. And then you return a p-value, which the way I understand p-value is it kind of represents the amount of surprise you will see in your data. The amount of surprise you can reason about the null hypothesis when the data you see is the data you see. And then based on the p-value, you reject or fail to reject the null. We never accept anything in testing. We always just reject or fail to reject. It's a very important concept. So what is a good testing procedure then? So an ideal testing procedure should give you small false positives and small false negatives. The false positives is the type 1 error. So it's the probability of rejecting the null when the null is true. And false negatives is the probability of failing to reject the null when the alternative is true. And however, in reality, it's difficult to have both type 1 and type 2 being close to 0. I mean, it's ideal, but there are trade-offs, right? It's just like classification problems. So we have different names for different scenarios. We say a test is valid if we can control the type 1 error. We'll specify a significance level and then say, if we have a procedure mathematically that can show that the type 1 error will be less than or equal to alpha, then we say this is a valid testing procedure. And we say this testing procedure is consistent if given infinite data, the type 2 error will go to 0. Okay, so hopefully I've reminded some of you that what testing is about. Then I'm going to focus on a specific type of test called two-sample test. Imagine now, again, I'm going to reason about, I collect some data from Germany, I collect some data from Japan, and then now I want to ask a question. Simply, are they from the same distribution? Or are the two distributions the same? Against the alternative that they're not. So in the ML literature, kernel two-sample testing is quite popular and quite used a lot for this kind of test because, first of all, it's non-parametric. So I don't need to assume any parametric form or density for P of X or P of Y. Second of all is kernel methods allow you to work with structured and non-structured data. You can have graphs, you can have strings, you can have images, you can have videos. As long as you can define kernels on top of them, you can do this kind of test. So a bit of reminder what kernels are. So we have a non-empty space, non-empty set X, and we can define a kernel on top. Then we can define something called the kernel mean embeddings, which is a mapping from the distribution to a vector in a function space or a function in a function space, which is given by this Bochner integral. And we can now, since you can imagine this mapping is trying to represent a distribution to a point in a function space. And since we now have, like if we have two distributions, we send them to 2 points in the function space, we can measure distance there. So the maximum mean discrepancy is an example of integral probability metric, IPM, is defined as follows. So the MMD square is the square RHS norm between two representations. So some of you might ask, if we don't know about P, then how do we know about mu P, and then how can we compute things? But nice thing is we can estimate mu P based on empirical samples. Yes, please.
Just one is just the absolute value of the difference between the integrals above, yes?
Yes. Yes. Yep. And yes, so basically we can, even though we don't have any assumption on the form of P, if we have samples from P, we can still talk about the similarity by doing some Monte Carlo estimation, and then we have this empirical MMD. But first of all, why is this good, or why is this useful? It's because, oh, sorry. It's because there are results showing that for popular class of kernels, this mapping is injective, meaning that as long as we can show MMD square is very close to 0, then it is very likely that P of X and P of Y or P or Q are actually very close to each other. However, we also know that, as I said just now, some properties on the kernels allow us to turn the pseudo metric into an actual metric or distance in probability space. So under the null, when P is actually Q, we know for sure the MMD will be 0. But because we're estimating this MMD with samples, it's not going to be 0. It'll be close to 0, but knowing, let's say we compute the test statistic and we get a number 0.3, we don't know whether it's small or large. So usually in testing, we need to compute the limiting null distribution of the test statistic. And with the limiting null, we know how much surprise we can quantify when we see the data. That's what the null distribution can be used for. However, in the case for MMD, this limiting null distribution converges to an infinite sum of chi-squares, which means it's not very useful for quantifying, using it to compute the p-value, for example. But because we are testing equality of distributions, which translates to we are testing exchangeability of data, there are some permutation procedures that allow us to obtain the rejection threshold or the p-value for the testing procedure. I'm not going to go into detail the permutation procedure, but I just want you to know that for two-sample testing, we can compute it pretty easily just by swapping samples, compute test statistic, and then look at the histogram, cut it off, done. Okay, so that's kind of the background. But what if we now face dataset uncertainty? So going back to our kind of like the proxy example, instead of collecting data from the whole Germany, I collect data from hospitals, 4 of them here, and then I collect some data from hospitals in Japan, and 3 of them. Now I'm willing to assume each of the observations from the hospitals are ID with respect to that hospital, but I think it's too strong to assume that they all, on the left-hand side, they all share the same distribution. So what can I do in this case? As I said, they're proxies of some underlying unknown P of X that we'll never have samples on, unless you're willing to pay a lot of money. So now we have dataset uncertainty. So the question will very naturally be, can I still make inference, or can I still do testing, or can I still do decision-making with respect to this dataset uncertainty? And if so, how should I represent this uncertainty in the first place? So when it comes to dataset uncertainty, there are a few giants that propose the same object to represent them. So from Wally perspective, I guess, I hope I'm not wrong, but in those area of people, they always say that subjective assessments of the lower bound of some probability, upper bound of some probability will always lead to some kind of closed convex sets of probabilities. Another field called quasi-Bayesian Bayesian decision theory, in those areas, they say that if an agent has partial order or partial preference over some objects, then extending from Savage axioms, they will have correspondingly a closed convex set of probabilities. So this basically means when you have indeterminacy in the preference, it corresponds to a set of probabilities. Lastly, from philosophy or epistemology, or they call themselves formal epistemologies, they basically have this axioms called this property called chance calibration, which says that according to your set of evidence, if you believe your current chance function, which is the actual P of X in our problem, it lies within a set of probability functions, then rational agents should express the uncertainty as the convex hull of what you have. So I hope I have convinced you that from 3 different areas of study, they all champion the use of closed convex set of probabilities. And this is what people call the Credal set. Okay, so what's going on here now then? On the left-hand side, we actually have samples from these physical or evidences, physical probabilities, like we actually have samples from the hospitals. However, we are gonna use what I've shown you just now to represent my belief over the uncertainty as a convex hull. And now I'm translating the aleatoric probabilities into a set of what I call epistemic probabilities. They're the beliefs. Now, then in this case, it's very natural to ask, well, since I can never compare P of X and P of Y, but I have proxies, I have evidences, can I instead compare my rational beliefs? And if so, how should I do it? So recall, in the classical two-sample test, we compare points in the probability space. That's exactly what the null hypothesis is about. The triangle you can think of as a probability simplex or the space of probabilities, doesn't matter. And in my work, I proposed 4 different null hypotheses that each of them makes sense in some case. So I call this the specification hypothesis, which asks whether a given P of X is inside a set of a Credal set. No, sorry, not inside a set of Credal set, it's inside a Credal set. The second hypothesis I care about is the inclusion hypothesis, whether one Credal set is completely inside the other. And this one is a strict generalization of two-sample test, so it's not that interesting, but I can still ask whether 2 Credal sets are the same. And I can ask whether 2 Credal sets actually overlap at all. And these hypotheses, each of them will have their own test. But for people who have worked with testing before, you see one test is actually a special case of the other. So it's possible to do some kind of like composite testing on this. So not only are we doing this because of intellectual curiosity, but there are actually some potential applications for these hypotheses as well. So for specification, we can ask that it can be used for OOD detection. Why? Because a lot of out-of-domain generalization, machine learning machinery, they will train the algorithm based on convexifying the set of distributions and then look at the worst case. In those scenarios, they're kind of assuming the deployment and distribution will be inside the convex hull. So in that case, you need a systematic procedure to verify or check this assumption. So that's what this OOD detection can be used for. And there's a growing field of Credal predictor that basically give you a set of predictions and then find some way to come up with a Credal set. In those cases, you also want to do some kind of testing to verify whether either some true distribution is captured by your Credal predictors or not. From a purely statistical perspective, you can understand specification tests as a non-parametric test for finite mixture models, which for some reason has never been done before. It's very surprising, but from a statistics perspective, you can also understand like that. For inclusion cases, it can be used for uncertainty comparison because uncertainty quantification metric for Credal sets, there are many of them, but they are not a unified perspective. However, they have this monotonicity axioms that says that if one Credal set is inside the other, then one inside must have smaller uncertainty, right? So why don't we just directly check whether it's inside or not? equality, as I said, is a strict generalization, so it might not be that interesting. But plausibility can be understood as a distributionally robust two-sample test. What do I mean by that? Is that imagine I reject the null in this problem. What it means is even despite my evidence, despite my uncertainty, I have enough evidence to say that if I'm willing to assume P of X is inside one Credal set, P of Y is inside the other Credal set, then despite the evidences, despite the ambiguities, there are enough evidence to tell me that they're never going to be the same. That's P of X is never going to be the same as P of Y, even if you have ambiguity in your hypothesis. That's what it means when you reject the plausibility hypothesis. But that's kind of like all intellectually interesting, but in practice, how do we actually design a valid, which means we have control type 1, and consistent testing procedures, which means we have diminishing type 2 error for all these tests. So we call Credal specification test. What's going on is we observe. So Credal specification is we have a point inside a Credal set or a point inside convex hull. What we are observing is this samples from the point and samples from the corners of the Credal set. So can we based on this find enough evidence to reject the null, which is the point is inside the set. So the high level idea is the following. If we know the point is inside the set, then the point can be represented as a convex combination of the corners, which is what this equation means. So now the question is, based on the samples, can we identify the correct mixing weights of the corners or corner distributions? The answer is yes, but we need some optimization technique. So therefore, it boils down to two-stage approach, a very natural two-stage approach. First is, after you identify the optimization weight or the convex weight, you can simulate pseudo samples by doing some kind of like sampling without replacement, blah, 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 to get pseudo samples from the now aggregated distribution. And based on the aggregated distribution, you can do a two-sample test for this setup. Like P of X equals to lambda transpose P of Y. So to do the optimization, we need to find an objective, right? We need to be able to measure, given 2 points in 2 Credal sets, what is the distance between them. To do that, we use MMD, maximum mean discrepancy, or because it's specific to Credal set, I'm calling this the kernel Credal discrepancies. So the arguments to KCD are 2 convex weights of the Credal set, because we're working with convex hull, so the convex weights uniquely identify that particular distribution. As I said, this MMD is trying to compute the RHS distance between 2 points there. And this, as I said, is the representation of distribution. And this representation has nice theoretical properties as well, meaning that it actually converges to the true thing, not too slow, root n, 1 over n. Yes, please. No worries.
So if the goal here is parameters eta and lambda, the goal is to find eta and lambda that minimize this MMD.
Yes.
The goal is to find them, right?
Yes.
So these are like the optimization variables.
Yes.
And this is under the assumption that Px equals lambda transpose y for some lambda. Is it not? This is under the assumption that Px is like some linear image of Py.
So the null hypothesis for this specification test is the same as saying P of X equals to some combination of P of Y. But this objective doesn't require that assumption. It's just an optimization. It's just a measure between 2 points in a Credal set. 2 points in 2 Credal sets, sorry. And maybe in the next slides, it will be more clear. So after some linear algebra, we can show that this KCD can be written as a quadratic objective. And if we set eta to 1, which means we are testing whether a point is inside a set, then this is a convex objective, which can be solved very quickly. And why is this useful at all? It's because under the null, when Px is inside Cy, it is an if and only if condition that when you minimize KCD, you actually can recover the parameter of interest, the convex weight. So this is why the assumption kicks in. So if you assume that P of x can be written as a convex combination of some y's or P of y's, then by solving this optimization problem in a population at the population level, you can recover the exact parameter. But in reality, we know that KCD is like a population quantity, so we need to estimate it with samples. Then there will be estimation error in the convex weights. So now, again, recall what I'm doing. We observe samples from point, we observe samples from corners. We call the first step epistemic alignment because alignment was a hot thing before. So what it means is we are solving the optimization objective to identify the convex weights. And the second part is we now have the weights. We can simulate some pseudo samples as if we have the true weights. But as in a lot of statistical procedures, we would usually do data splitting because otherwise the first step and the second step will have unwanted dependency and it affects our analysis and it's not as nice as just assume, just do some sample splitting. Okay, yes. So usually people will either split the data set into like 50-50, where the 50 is used to do, let's say, the optimization, and then the rest of data is being used for testing. But an interesting things happen now. But yeah, we call the overall strategy is we have samples, we split them, we solve optimization with one set of them, and then we simulate some pseudo samples and do testing for the other set. But when we do sample splitting, we actually have a non-valid testing procedure. What I mean is I have already specified, let's say 0.05 is my type 1 level. My testing procedure will always get inflated. And this is very interesting. This inflation doesn't disappear as you increase samples. So what it means is I'm only doing estimation, and then using the estimated parameter, I'm doing testing. Supposedly the testing procedure should work, but then we are not. It is not working. It has inflated type 1. The reason is very interesting is because of the estimation error from the first procedure. Okay, so on the figure, you should be expecting a completely overlapping distribution there. But you see a shift, and this shift is because of the estimation error that happens in the first stage. Okay, so don't forget the big picture. We need a correct type 1 control to have a valid test. Otherwise, we cannot deploy the test in practice. But we are not getting that. And that is because of the estimation error. So how should we fix it? Turns out we can fix it by using what we call an adaptive splitting protocol or procedure. And why does this adaptive splitting procedure works? So adaptive splitting means when you give me a data set of size n, my splitting ratio would depend on the size n. So don't want to bother you with uninteresting theorems, but the idea is that the error in the test statistic goes to 0 based on this ratio, NT, number of testing points divided by number of estimation points. So if this ratio is constant, which means you split your sample with a fixed ratio, then your test statistic error will never go to 0. This means no matter how many samples you have, you do sample splitting in a fixed way, you do estimation, you do testing, you will never approach the right quantity you care about. But if you now can choose a sample splitting adaptively such that NT divided by NE goes to 0, then this error goes away. Then it is as if you have done the test with the true parameter that you care about. So this kind of one theoretical contribution we have in this paper as well for testing with estimated parameters. And then a small result there is saying that, well, under the alternative, the test statistic goes to infinity, so we will be able to reject the test all the time, which means we have like a 0 type 2 error asymptotically. Okay, so just now I go through the high-level procedure how to do the first test. There are 3 other ones. I don't have time to go through it today, but the idea is not too complicated. The math for the last one is very interesting because we know the KCD objective when we fix one parameter is convex. But when we have 2 parameters, it is actually a biconvex optimization, which doesn't have global minimizer, which means every time we run the algorithm, we do this fixed one and then convex, fixed one and convex. We do this alternative minimization. We might land at different pairs of lambda and eta, but we still manage to prove its validity. And the ideas behind are quite interesting. So feel free to have a read if interest. And we have some experiments showing that our approach actually works. And it's solely from the testing perspective that if you have a test that involves some estimation of parameters, there are 2 existing methods on this, and we beat them significantly. They are the results from here. So they're performing quite poorly. Yeah, and as you can imagine, we can choose the splitting ratio differently. And it is interesting because if you choose the splitting ratio that puts more weight on the estimation, then you have a faster convergence to the right type 1 error. But because you'll be using less samples for testing, your power, which is the 1 minus type 2 error, will also be smaller. We also have some experiments on ELLIS data, and to show that we actually can do real-world data. And that's it. So the takeaway is hypothesis testing, especially 2-sample testing, is a fundamental procedure for evidence-based decision-making, but it's limited to precise distributions only. But nowadays, because of the abundance of data, there could be dataset uncertainty. So how should we adapt, represent, and propagate this uncertainty into the testing procedure itself? And I propose 4 null hypotheses to do these kind of problems. And yeah, so that's kind of the contribution of this work. We also have some other work in the group that also apply some ideas from IP to some machine learning problems. For example, prediction or learning, when you don't know which data set you're going to apply to when you deploy a model. We recently also, it's not archived yet, but we are still working on it for revising it. But it's for the case of proper scoring rule, truthful elicitation type of problems. And this is our lab. And I'm moving to Singapore soon, so this will be the people I'm working with. And thank you for coming. Yes.